The universe was supposed to be predictable. For decades, scientists believed they had finally decoded the rulebook of reality, a framework so precise, so consistent that it could rewind time itself back to the first seconds after the Big Bang. This framework, known as the Lambda CDM model, didn't just explain the universe, it predicted it. It told us how galaxies should form, when the first stars should ignite, and how light itself should spread across the cosmos. And for a long time, it worked, until something showed up that wasn't supposed to exist. When the James Webb Space Telescope powered on and began peering deeper into space than any instrument before it, scientists expected refinement. Sharper images, better data, minor corrections. What they found instead was disruption. Hidden in the earliest epochs of the universe less than 1 billion years after the Big Bang were massive structures that didn't behave like galaxies at all. They had the mass, they had the gas, they had the gravitational signatures, but they weren't shining. No stars, no light. Just enormous, invisible structures drifting in the dark. These are what some researchers are beginning to call dark galaxies. And their existence creates a problem so fundamental, it threatens the timeline of the universe itself, because according to everything we thought we understood, this shouldn't be possible. To understand why this is so unsettling, you have to go back to the beginning, not just of the universe, but of our understanding of it. The Lambda CDM model is built on a simple idea: structure forms in stages. First comes dark matter, an invisible substance that makes up most of the universe's mass. It clumps together under gravity, forming what scientists call halos. These halos act like scaffolding. Then comes gas, mostly hydrogen falling into those halos. As it collapses, it heats up, compresses, and eventually ignites nuclear fusion. That ignition is the birth of stars. Stars light up galaxies. Galaxies cluster into larger structures. Over billions of years, this process builds the universe we see today. It's a clean sequence. Cause and effect. Gravity leads, light follows. But what happens if the light never comes? That's the mystery. Because what James Webb Space Telescope is now detecting suggests that in some regions of the early universe, the process stopped halfway. The dark matter halos formed, the gas accumulated, but the stars never appeared. Imagine entire galaxies that never turned on. No fusion, no illumination, just cold hydrogen clouds suspended in gravitational wells, massive enough to be galaxies, but completely invisible to traditional observation. This isn't just unusual, it's destabilizing, because if stars aren't forming where they should, then our understanding of when they form and how efficiently they form starts to break down. And that leads to a much bigger question: what else are we getting wrong? The conflict here isn't just about missing stars, it's about timing. The early universe, as predicted by our models, was a chaotic but highly productive era. Gas was dense, conditions were extreme, star formation should have been rapid and widespread. In fact, one of the biggest surprises from James Webb Space Telescope has already been the discovery of galaxies that are too massive, too bright, and too evolved for their age. Some galaxies appear to have formed hundreds of billions of stars far earlier than expected, almost as if the universe accelerated its own evolution. But now we're seeing the opposite problem too, regions where star formation seems delayed or suppressed entirely. So on one side, the universe is evolving too fast. On the other, it's not evolving at all. That contradiction shouldn't exist. It's like watching a movie where some scenes are playing in fast forward, while others are frozen in time. And both are happening simultaneously in the same cosmic era. So what could cause this? One possibility is that we're underestimating the complexity of star formation itself. Forming a star isn't just about having gas and gravity. The gas has to cool, it has to fragment, it has to reach the right density under the right conditions. And in the early universe, those conditions were influenced by radiation, turbulence, and feedback from nearby structures. It's possible that in some regions, intense radiation from early galaxies prevented gas from cooling efficiently. Without cooling, the gas can collapse. Without collapse, no stars form. Another possibility points to something even more fundamental: dark matter. The entire structure of the universe depends on it. But we still don't know what it is. If dark matter behaves slightly differently than we expect, if it interacts, decays, or distributes itself in non-uniform ways, it could change how galaxies form at the smallest scales. Some theories suggest that certain types of dark matter could prevent gas from condensing in smaller halos, effectively creating failed galaxies. Galaxies that had the blueprint, but never completed construction. then there's the possibility that what we're seeing isn't a failure of formation but a limitation of observation. These dark galaxies might not be completely dark. They could contain faint, low-mass stars that are simply too dim to detect, even with our most advanced instruments. Or they might be obscured by dust, hiding their light behind thick cosmic veils. But even if that's true, it doesn't fully resolve the tension, because the number, distribution, and scale of these objects still challenge the predictions of the Lambda CDM model. And that brings us to the deeper issue. This isn't just about galaxies. It's about the reliability of the model we use to describe reality. Cosmology is a field built on indirect evidence. We can't run experiments on the universe. We can't rewind time. We observe, we infer, and we construct models that best fit the data. And for decades, the model has held. But now, the data is getting sharper, and the cracks are becoming harder to ignore. The discoveries from the James Webb Space Telescope are forcing scientists into a position they haven't been in for a long time. Uncertainty. Not the comfortable kind, where answers are just out of reach, but the deeper kind, where the questions themselves might be wrong. Because if galaxies can exist without stars, if structure can form without illumination, if the timeline of the universe isn't as clean as we thought, then the story we've been telling about our origins might be incomplete, or worse, partially incorrect. And yet, this is exactly how science moves forward. Not by confirming what we already believe, but by confronting what we don't understand. Every anomaly is a signal. Every contradiction is a clue. The dark galaxy problem isn't just a flaw in our models. It's an opportunity, an opening into a deeper layer of reality that we haven't fully explored, because somewhere in these invisible structures, in these silent, starless regions of space, there is information. Information about how matter behaves under extreme conditions. Information about the true nature of dark matter. Information about the earliest moments of cosmic history. And perhaps information about limits in our assumptions, in our models, and in our understanding of the universe itself. Right now, we're standing at the edge of that unknown, looking into regions of space that don't glow, trying to understand objects that refuse to reveal themselves, and asking a question that is both simple and profound. What if the universe doesn't follow the rules we wrote for it? Because if that's true, then this isn't just a discovery, it's a rewrite, not just of textbooks, but of reality itself.